Now we can do the same thing with more complex molecules. So we could start with butane. And you could say if I'm looking down the C2 to C3 bond, which means that C2 would be in the front, C3 would be in the back. And you can draw all the Newman projections that are possible for that structure. So if I do that, what you'll see is if I start in the front, so you need to add the other atoms in if you can't do it in your head. Say, okay, so what else is on this carbon? So I'm looking down this bond. So this is front, this is back, right? So there's my back carbon. So what do I have on the front carbon? I've got 2 hydrogens and a methyl. Now, you can put them anywhere that you want to when you're drawing it, the first one. So I'm just going to choose, I'll put my methyl straight up and my 2 hydrogens down into the back. So that's the front carbon. And then the back carbon, again, you can put things wherever you want to. So I'll start with it completely eclipsed with my CH3 also going up, my hydrogen coming to the side, my other hydrogen coming to the side. This is an eclipsed structure. Now, anytime we draw structures, there are going to be 6 structures to draw. Some of them may be identical, but we always will have 6 structures, because if I hold one of them in place and don't move it, and I rotate the other one, there are 6 different positions that I can rotate around until I get back to the original position. So I start with this one eclipsed, and then I'm going to keep one of them the same. For the sake of this, I'll keep the front one the same. And I'll keep it the same for every single structure that I draw. The reason I do that is that that helps me make sure that I haven't made mistakes by changing 2 things at once. So I'm going to draw all 6 of them with that front carbon exactly the same. And then I'm just going to rotate the back carbon each time, 1 space. So I start eclipsed. My next one, if I rotate this around this way just a little bit, will become staggered. And if I keep rotating, my next one, it will be eclipsed. My next one, it will be staggered. My next one will be eclipsed again. And my last one will be staggered. So I'm just going to write eclipsed, staggered. After that, I'm just going to write a letter, E, S, E, S. Eclipsed, staggered, eclipsed, staggered. However, all 3 of these eclipsed ones are not identical. In this first one, I have methyl eclipsed. While in the other 2, I have methyl hydrogen eclipsed. So now you have to decide which of those 3 seems like it will be the worst steric interactions and then be the highest energy. The eclipsed ones, of course, are always higher energy. The staggered ones are always lower energy. So hopefully you guessed that the first one is going to be highest energy. It has the 2 largest groups eclipsed, so due to steric reasons. That's the highest energy. And then the next 2, these 2, are both high energy, and they're both equivalent, but they're not the highest. So this gets into the idea of sort of a global maximum versus these ones, which would be local maxima. if you're graphing. Now let's look at the staggered ones. When things are staggered, if you've got two big groups nearby each other, this is called a Gauche interaction. And Gauche interactions, while not as large as eclipsed interactions, are still bad if we have our two large groups gauche to one another. Okay, so in this case, I would have it staggered gauche. In this one, however, the two big groups, one is straight up and one is straight down. This would be staggered anti, because they're anti, or they're opposite each other. The two big groups are opposite each other. In this next one, it's also staggered gauche. So you should try to determine between those three which is going to be the overall lowest energy. So I hope that you would think that it would be the staggered anti. Due to sterics, the two largest groups will want to be as far apart as possible. Staggered gauche, they're still nearby each other and they're still causing interactions. So this will be our global minimum. And the other two staggered will be local minima. And again, these two are the same. They both have one staggered gauche interaction. So now you can actually draw a graph of energy on the y-axis versus rotation around that carbon-carbon sigma bond on the x-axis. So if you want to start down here, we could have staggered anti. I'll just do letters on these. And after staggered anti, goes up through a rotation to an eclipsed, but it's only methyl hydrogen eclipsed, so eclipsed with a hydrogen in it. Goes down here to another staggered, but it's the staggered gauche now. Goes up here to an eclipsed, which is the methyl-methyl eclipsed. Comes back here to another staggered gauche, and then goes back up here to another eclipsed, where it's methyl hydrogen eclipsed. So there are 6 positions. Lowest energy, staggered anti. Highest energy, methyl-methyl eclipsed. And then the other eclipsed are always high, the other staggered are always low. So this is what I mean when I was talking about before, that you could have a global minimum versus a local minimum. So a minimum is any time that we have a valley, that's a minimum on our graph. The global minimum is the overall lowest for the whole graph. We can have a local maximum, and then we can have a global maximum. That's the highest energy for the whole graph.